that means. On the test, I think something that people missed a lot was they didn't read the question. Alex lets you draw either a skeletal structure or a condensed structure. You need to know the difference, and you need to read the question, and you need to answer. Is it asking you to draw the skeletal structure, which is what we're going to talk about today, or the condensed structure, which is what we talked about last time. So last time we didn't draw the hydrogen bonds, the bonds between hydrogen and carbon. We didn't draw the lone pairs on oxygen and nitrogen. That was condensed. Today we're going to do skeletal structures. So just watch out, read the directions. Okay, the other thing we're going to look at is where are the hydrogens. We're going to practice looking for hydrogens in a skeletal structure. So there's a few more slides than last time, but we should still be done with lots of time. So a skeletal structure is just a simplified model of an organic compound, and we leave out the hydrogens. We also leave out the oxygen or the carbons. So every time we draw a corner, that's a carbon. So when we look at some examples, I think that will make more sense. So we're going to assume there's a carbon atom at the junction of any two lines. So if it's like the lines cross, there's a carbon in the middle. Or if there's like a corner. So corners and where the lines cross, that is a carbon. And then around every carbon, remember that carbon has to have 4 bonds. So any bonds that are not shown, to fill the octet, carbon has to have 4 bonds. All those extra bonds are hydrogens. So this is where we have to kind of do some imagining. So if we don't have enough hydrogens, it's because they're just not there. They're still there. They're just not shown. They're not drawn. In a skeletal structure, we do draw oxygen and we do draw hydrogens directly bonded to those heteroatoms. So if there's a nitrogen, it could have 2 hydrogens on it. We're going to show those. We just don't show any hydrogens bonded to carbon. And again, I think if we look at some examples, it'll make more sense. Bless you. So I think the most important thing to remember when we're talking about skeletal structures is each carbon has 4 bonds. So if it's not shown, you got to kind of imagine and count. Oh, this has 2 bonds. There must be 2 invisible hydrogens. And this is kind of weird, but the more you see these, the more familiar you get with them. The more you practice in Alex, the easier this will be. I always think of this as like, if you meet a new person, the more that you talk to them, the more that you see them, the more that you say their name, hopefully you remember their name and lines up. But you start picking up on their name. I recognize you, I remember you. So it's kind of like that. All right, I think, are we ready? I can't. Sometimes I just can't tell if you're ready. Okay, so here's this is the full Lewis structure of cyclohexane. In chapter 13, we'll practice naming cycles. This is the cyclohexane. This is a skeletal structure. So can you see how this corner, that's a carbon. This corner is a carbon, that corner is a carbon. So this is much simpler. That's why we use a skeletal structure, because if we're writing a paper, this is just really easy to draw, or really easy to see. I know what that is, that's cyclohexane. There's nothing else on it. The other thing that you need to look at is we erased all the hydrogens. They're still there. So if I look at this carbon, it has 1, 2 bonds. So it still has those 2 hydrogens here. They're still there. We have to imagine them, but they're still there. So, does that make sense? So this is where it takes practice. You have to practice identifying. Oh yeah, there's hydrogen there. Don't forget that those are there. Okay. So then this is what I was talking about. If we have a heteroatom, so a heteroatom is something that's not carbon, not hydrogen in our organic molecule. So this is cyclopentanol. We don't draw the lone pairs. We don't draw any hydrogens connected to carbon, but we draw the hydrogen connected to the heteroatom, or this, in this case, it's an oxygen. We draw that. So when we're looking at this carbon has a bond to an oxygen, has a bond to another carbon, has a bond to another carbon. It has to have 4 bonds, so that missing bond is the invisible hydrogen. So we see it here. When we draw the skeletal structure, we don't show that. Does that make sense? Okay. So if you need to, go back and review the notes if you forget. You can also just, this is something to practice in ALEKS. I think that's, the more you see of these different molecules, the more you can see this pattern. Oh, if there's 3 things bonded to the carbon, there's 1 hydrogen hidden. Okay, when we draw, so this is when we're drawing a linear structure. So we have our full-blown Lewis structure. And then what we're going to do is, if it's an end, that's a carbon. And then every time we have like a corner, that's what I call them, I don't know. So an end is a carbon, a corner is a carbon. So here we have, if we count this, let me turn on our pen. Oops. So here we have 1 carbon, 2 carbons, 3 carbons, 4 carbons, 5 carbons, 6 carbons. So what they've done is they've done 1, 2, 3, 4, 5, 6. And this represents what is actually happening in the molecule. So our molecule of, this is hexane, is not actually linear. It can spin around these single bonds, and so it ends up looking more like, I don't know, like a sideways stairs, like a staircase almost. So we draw it like this, our skeletal structure like this, because the molecule is actually more like this. Because, do you remember, around a carbon, what is the bond angle? Or the shape? What shape do we call that? So carbon has 4 bonds. So the bond angle is 109.5. And that's going to be a tetrahedral. So every one of these carbons is tetrahedral. And so that's why it makes this kind of jagged shape. Okay. And that's why we draw it like that. It just looks more like that. Okay. Questions on that? All right, so some of the things that you have to do in the homework is that you have to draw these chemical structures, and ALEKS is really picky. So these are some things that will help you when you're drawing bonds in ALEKS. So ALEKS really cares that you have this 30-degree angle from the horizon for your carbons. So for your carbon chain. So if you do something like this, and then you put your NH2 over here, it will not like that. Can you see how that's like too steep? So if it's marking it wrong, and you think you have the right number of carbons and other atoms, ALEKS is really picky about making it beautiful. So that's something that you want to check. You want to make sure this is an obtuse angle, and this one is an acute angle around 30. Okay, and that just takes some practice. The other thing ALEKS really likes is that if you have this on this side, then you should draw, as much as you can, you should draw it to look the same as the condensed structure. So this one, we have 1, 2, 3, 4, 5. So this is 1, 2, 3, 4, 5 carbons, and then we have a branch, 2 carbons coming off. So we can do like I don't know, we'll call this one N2. So we want to show it's like pretty similar. Does that make sense? Okay. And then can you see this one still? If you have something coming off, you want it to go straight up. I think that might be on the other side. But this is a branch coming off. The branch needs to go straight up and then have an obtuse angle here. Okay. And that's, again, if you practice in Alex, it'll help you. Okay. Okay, yeah, this is what. So I guess you can think of this as a 120, or I like to think of it as just like it's going straight up. If you draw your chain, then the substituent, the group coming off the branch, is going to go straight up, or 120 degrees from the main chain. If you have two substituents, so like this one, we have, let's draw our carbons. We have 1, 2, 3. Oxygen is the 3, 4. So we've got 1, 2, oxygen's the 3, and then we have our 4th carbon. This carbon has 2 branches off of it. So we don't put the carbon coming down. That's wrong. Let's see if there's like a erase. Yes, we are erase button. Okay. We put them both coming off of the chain, and they're like 60 degrees apart. And that represents more of a tetrahedral angle than something coming straight out of the bottom. So this is just like convention. And Alex will mark you wrong if you don't do it according to convention. Okay, questions on that? And these do come up. So again, this is something if you practice in Alex, you're pretty comfortable with how Alex does it. It'll be much easier. But it is a little bit frustrating at first. When I was practicing for the first time last year in Alex, I was getting frustrated with figuring out, because Alex is very picky when you're drawing these. On the test, if you do it correctly, the only thing is your bond angles. I can go back and give you points, but you have to get through the homework. So on the homework, you need to be really careful about drawing just like Alex wants it. Okay. All right. Okay, this is the last part, and it's a little bit confusing. So if we have a double bond carbon, and we have 2 groups on the same side of the double bond, these groups technically cannot rotate. So this would be a completely different molecule. These are, and we'll talk about that in chapter 12. But while we're practicing in chapter 11 drawing these, we just need to know that if these show up on the same side of the double bond, so like this, what I mean by side is I'm cutting my molecule in half according to the double bond. These are both on the top of the molecule. Nothing is on the bottom. Okay, you see that? So these are on the same side. So when I draw my molecule, I have carbon 1, 2, 3, 4. This is carbon 1, 2, 3, 4. These both need to be on the same side. So this would be like the top of the molecule. This would be the bottom. And again, we'll talk about this. This is a completely different molecule that has different properties. This is the top. This is the bottom of the double bond. So they're on different sides of the double bond. So this is a different molecule. When Alex shows you this, you need to draw the things on the same side. Does that make sense? Okay. And the reason for this is that I don't think I have any molecule sets out. But the double bond locks the carbons together. And this has to do with what orbitals are bonding. So this is a little bit beyond us, but when you're making a double bond, the 2 p orbitals will bond together. And so then the geometry of the orbitals lock that bond in place. And so it takes some energy to flip to a different molecule. So this is locked. All of the carbon-carbon bonds can spin. And in chapter 12, we'll get out some models and we'll talk about this. But the double bonds can't spin. So, like, think about the bond, you can spin a bond around the center. Well, the double bond you can't spin, so that's why those are locked. Okay. And this is a pretty simple molecule as an example. They did get a little bit trickier in the Alex homework. So we'll do one side where we practice, and then the rest of the time you can practice in Alex. So in the same sense, if they show you a molecule where the OH and the OH are on opposite sides, then you're going to want to draw the one where they're on opposite sides. You just have to make sure that you're matching what example you give. Okay, so go ahead and try to draw these. And then we'll draw them as a class. So, we're drawing the skeletal structure. Draw the skeletal structure. I should probably put that on my slides. Draw the skeletal structure. Okay, so try to remember we're not showing hydrogens. Carbons are corners or ends. Throw something down. Sometimes the hardest thing to do is just start. Try to draw something. Oh, I think we have one more. You don't put the H's or the carbons. So the carbons just become corners. You do put the hydrogens on the nitrogens and on the oxygens. But yeah, your shape will be good. The shape of it. Yeah. Yeah. So you have to go either way. Oh, so dogs will be the wider. There you go. Yep. Yep. Okay, let's go ahead and draw these. I think we're getting the hang of it. So I'm just gonna, it helps me to label the carbons, to count them. So you can count them in your head. I'm gonna count them on the board. And then we have 2 groups coming off of carbon 2 and then a 2 carbon chain coming off of 3. So, and also the other thing is like, if I start like this and you start like this, does that make sense? Like, that's the same molecule. That's okay. Does that make sense? So don't worry about that. Worry about like the pattern that you're seeing. Okay, let's go back. So here, I'm going to draw this nitrogen. And we do draw the hydrogens off of the nitrogen. Or an oxygen. Okay, I'm just going to go up, so that's 1. I'm going to go up to carbon 2. And I'm just going to draw the main carbon chain first. So 2, and then the 3rd piece, the 4th piece, and mine are probably not wide enough. Alex probably wouldn't like that very much. So 1, 2, 3, 4, 5. So the carbon at the end is just by itself. So 1, 2, 3, 4, 5. Okay. And then we have 2 groups coming off of this first carbon. They're going to be pointing whatever way this is pointing. So they would be pointing up if there was only 1, but there's 2. So remember, our rule is that we need to have about 60 degrees between them. And they're both, remember what this group is called? CH3? What group it is on your, I don't think I have my paper out yet. It's called a methyl group. Does that sound familiar? Okay, so if I have a CH3 group, that's methyl. So I have these 2 methyl groups pointing off of carbon 2. And then we have this carbon, on carbon 3 we have a carbon group. So what we're going to do is that's going to come off pointing down and then go over. So what carbons like to do is form this cyclohexane. So besides when there's 2 groups coming off of the same spot, generally they're going to try to, we draw them in the cyclohexane shape. You can buy notebook paper instead of grids that is cyclohexane to help you draw your organic molecules. So that's kind of fun. So that, now we're done. Now we have these 2 branches, we have these 2 methyl groups, we have all of our carbons. So that would be our skeletal structure. This would be a condensed structure, so you have to know the difference. When the test asks you to do the condensed structure, oh sorry, this is the condensed structure, this is the skeletal structure. So be really careful about what it's asking you for. Okay, this one, let's go ahead and label. We've got 1, 2, 3, 4, 5. So I'm going to do the carbon chain first. And then notice we have 2 groups. They're on opposite sides of the double bond. So when I draw them in the molecule, they need to be on opposite sides. So I like to go from down to up. 1, 2, 3, 4, 5. Okay, that's also a pattern. If you notice, it's an odd number, so it points the same way. If it's an even number, it'll point opposite ways. That's a pattern you can watch for. Okay, at carbon 3, we have a methyl group that goes down. And here we have a double bond. So this one works out pretty easy. This needs to go on the opposite side of my double bond. So now this would be that molecule. They're opposite of the double bond. One's on the top of the double bond, one's on the bottom. Okay. Does that go okay? Okay, all right. I think we have one more slide. We're going to practice finding the hydrogens.
You come on understanding it now.
Okay, good. Good. Okay, so remember, even if we can't see the hydrogens in the skeletal structure, they're still there. You need to be able to identify them. And I just use the count to 4 rule with carbon. So let's just go ahead and let's go through this together. So if I'm looking at this carbon, how many hydrogens are there? Not 2. You're close.
3.
There's 1. So if we look at this carbon, we have a chlorine group, or we have a chlorine bonded, and then we have this carbon is bonded twice to this other carbon. And so the last one is hydrogen. Okay, I think this was the most missed question, so make sure you practice this one. This carbon, we have 1, 2, 3 bonds, so we must have just 1 hydrogen. This one, and so I just counted 3. 1, 2, 3, or 4. 1, 2, 3. The fourth one must be a hydrogen. This one has 1, 2, 3 bonds. The fourth one must be hydrogen. That doesn't really look like a hydrogen. It's a hydrogen. Okay, you follow that? Okay. Okay, that's a nitrogen. Nitrogen, remember, has 3 bonds, so that's 1, 2, 3. That's good. Okay. So this carbon, how many hydrogens are there? Good. 1 hydrogen off of this carbon. How about this hydrogen? Or how about this carbon? This one. Good. Okay, let's come over to this one. Has all sorts of different ones. This is a carbon on the end. How many hydrogens are attached to that one? Yes, good. So we have 1, and then the 3 to make 4 is these are all hydrogens. And this is another methyl group, a CH3 group. And so this is really symmetrical. So this looks just like that. This is going to have also 3 hydrogens. And then we have 4 bonds around the carbon. The carbon is happy. How about this one? Good. 2 hydrogens. So again, we can count. We can go 1, 2. There's 2 bonds shown. Those 2 that are missing must be hydrogen. Okay, let's go back 1. I forgot this one. 1, good. That's the hardest one for me when it's like on a corner. I forget that there's a hydrogen there. So that's also here. We have 3, so that one that's missing to get us to 4 is the other hydrogen. And then this is symmetrical. This has 2, 3, 4 bonds. And then over here, how about this one? 1, good, 1. And this one has 1. Okay, you think you could do that on the homework? Okay, all right, that is our slides. We have about 35 minutes of class. So work on either lab 13. I think I have those graded. If not, I'll check really fast and grade the ones that you submitted. So you can do corrections for lab 13. You can turn it in. Lab 5 pre-lab, that's what you're going to do next time. And then the chapter 11 Alex. Or you can do the signature assignment, or you can review for the final. So there's lots of things to do.